Something changed after perihelion. At first, astronomers thought it was just another routine data anomaly, a trick of light, a calibration error, a misalignment in the sensors. But then the images started to stack, frame after frame, telescope after telescope, and what they revealed has left the global astronomy community stunned. The newest photos of 3I-ATLAS, captured just days after its closest pass to the Sun, don't show a fading rock drifting into the dark. They show the opposite. The object brightened, its light didn't scatter, it sharpened. Its core began to split into structured spectral layers that no existing model can explain. And around it, the chaos we expected from boiling plasma began to arrange itself into order. In these images, the surrounding dust doesn't behave like dust. It moves in patterns, symmetrical, rhythmic, almost mechanical. What we're seeing may not be the death of an interstellar object. It might be its awakening. Tonight we're breaking down what these photographs reveal, what the data is hiding, and why several major observatories, from Mauna Kea to Paranal, are quietly rechecking every frame, frame by frame, pixel by pixel. Because if these readings hold, they don't just challenge our understanding of comets or plasma physics, they challenge our idea of what light itself can do. Before we begin, make sure you're subscribed, because this story is evolving faster than anyone predicted, and new data is being released almost every night. Hit that bell icon so you don't miss the next update as the world's most advanced telescopes turn back toward 3I-ATLAS. And while you're here, tell me in the comments, where are you watching from, and what time is it right now where you are? Because as you listen to the evidence tonight, and as we analyse each new image line by line, you'll begin to understand why some scientists have started whispering a phrase they were never supposed to say out loud. That 3I-ATLAS may not simply reflect sunlight, it might be controlling it. Stay with me. What you're about to see could change everything we thought we knew about how light, matter, and motion interact in deep space. This is the 3I-ATLAS channel. Calm, focused, and based on verified solar system telemetry. If you want to be part of this mission, hit subscribe right now. Comment ATLAS below to join the Data Watch and enter our exclusive 3I-ATLAS hoodie giveaway. Tell us where you're watching from and the exact time where you are. When an interstellar object reaches perihelion, the closest point to the Sun, it experiences the most extreme conditions any natural body can endure. Temperatures can rise above 1,000 degrees Celsius, solar radiation pressure peaks, and any remaining volatiles trapped within the surface begin to vaporize violently. For most comets, that moment marks the beginning of decline. They flare, fracture, and fade as their energy dissipates into space. But 3I-ATLAS didn't follow that script. The moment after perihelion, something changed. Images from the Solar Orbiter's heliospheric imager, captured just 6 hours after the object cleared the solar limb, showed a residual glow that refused to fade. Instead of a decaying tail and cooling nucleus, the brightness curve spiked, subtly at first, then unmistakably. The coma surrounding the object didn't expand chaotically as expected. It contracted, forming what appeared to be a concentrated sheath of plasma wrapping around the nucleus like a shell. That behavior is unprecedented. In conventional cometary physics, outgassing produces a diffuse halo of gas and dust that gradually thins with distance from the Sun. Compression of that halo implies a force acting inward, not outward, a containment field of some kind, or a feedback process we've never documented before. Spectral data from ALMA in Chile confirmed a second anomaly. The thermal emission profile didn't match the visible light curve. Normally, a brightening comet emits strongly in the infrared, as sublimating ice and dust radiate heat. In 3I-ATLAS, the opposite occurred. As the visible spectrum intensified, the infrared signal dropped. It was cooling while appearing to brighten. In physics, that combination shouldn't exist. When something glows more while losing heat, it suggests a non-thermal emission, luminosity generated not by temperature, but by energy reorganization at the atomic or magnetic level. Teams at the European Space Agency cross-checked the timing with solar flare data to rule out interference. Nothing matched. The Sun had been quiet during those hours. The illumination was internal. Some researchers suggested electrostatic discharge, similar to a St. Elmo's fire phenomenon, but at a scale far beyond any laboratory precedent. Others proposed photonic scattering caused by metallic compounds, nickel, cobalt, or even charged carbon structures reflecting sunlight in a coherent pattern. Yet the phase angles measured by multiple observatories didn't align with a simple reflection model. The object appeared to emit light anisotropically, meaning in preferred directions, almost as if responding to geometry rather than temperature. Another peculiarity lay in the timing. Perihelion occurred at 03:17 UTC on October 30th, 2025. Within 40 minutes, 3I-ATLAS had already regained 60% of its pre-perihelion brightness, a recovery far faster than any known comet. Most objects fade exponentially as they move away from the Sun, their energy sources exhausted. This one behaved like a capacitor discharging and then recharging again, drawing energy not from proximity to the Sun but from interaction with it. When the first post-perihelion composite was processed by the team at the National Optical Infrared Astronomy Research Laboratory, an unexpected symmetry appeared across the coma, concentric wave fronts radiating outward, evenly spaced like ripples frozen in time. Computer enhancement revealed that these rings weren't artifacts of image stacking. They were real gradients of luminosity. Their spacing suggested a periodic release of energy roughly every 9 minutes, correlating with faint radio pulses previously logged at 1.44 GHz. The implication was staggering. The optical and radio data might be coupled, forming a multi-band signature of activity deep within the nucleus. Scientists are cautious with language, but one internal memo leaked from the Cerro Tololo Observatory described the phenomenon as a structured response to solar input. Not a reaction, not random volatility, but a response. In that brief window after perihelion, 3I-ATLAS seemed to cross an invisible threshold, from behaving like matter to behaving like mechanism. Whether that mechanism is natural or engineered remains unknown. But in those first hours of recovery, it redefined what astronomers thought a comet could do. The Sun had not destroyed it. Instead, the encounter appeared to have awakened it. When 3I-ATLAS emerged from behind the solar glare in early November 2025, observers expected the light curve to follow a simple, predictable pattern. A sharp rise toward perihelion followed by a smooth decline as the object cooled and drifted outward. Every known comet follows that sequence. Energy input peaks near the Sun, volatile ices sublimate, and once the heat source diminishes, brightness fades exponentially. But what the telescopes recorded defied that law entirely. The first brightness data points came from NASA's Solar Terrestrial Relations Observatory, which tracked the object in the visible spectrum as it cleared the Sun's limb. Instead of falling off, the magnitude climbed. The visual intensity doubled within 36 hours of perihelion and continued climbing over the next 3 days. By November 3rd, the apparent brightness was nearly 3 times higher than any pre-perihelion prediction model. To understand how strange that is, imagine a comet releasing energy more efficiently after leaving the heat source that powered it. The equations of thermodynamics leave no room for that inversion. Astrophysicists at the University of Hawaii tried to explain it with delayed outgassing. Perhaps subsurface pockets of volatile compounds were still venting, releasing material that had been superheated but trapped beneath a dense crust. Yet spectroscopy didn't support that hypothesis. There was no surge in typical cometary gases, no corresponding rise in water, carbon monoxide, or cyanide bands. The increase in visible luminosity came without the chemical fingerprints of evaporation. The object was getting brighter without getting leakier. The second anomaly lay in the colour index. Standard comets redden as they cool. Dust dominates reflected light, scattering longer wavelengths. 3I-ATLAS, however, turned bluer with time. Between November 1st and 5th, the BV colour index shifted negative, implying that the emitted light carried more energy per photon even as the object receded from the Sun. That pattern is characteristic of ionized plasma rather than sunlight reflection. It's as if the nucleus was surrounded by a self-luminous sheath, radiating energy independently of solar reflection. Cross-checking from the Very Large Telescope and the Pan-STARRS array confirmed that this wasn't an optical illusion or instrument calibration issue. The photometric calibration against nearby stars was solid. Every frame agreed. 3I-ATLAS was brightening in defiance of distance. A few researchers floated exotic but testable ideas. One was photonic coherence. light amplification through aligned crystal structures in the object's outer crust. If certain minerals had reorganized under extreme solar heating, they could scatter sunlight more coherently, effectively turning sections of the surface into micro-lenses. Another proposal involved magnetoluminescence, a process where changing magnetic fields excite atomic states and release visible photons without corresponding thermal emission. The object's residual magnetic halo, measured faintly by the Parker Solar Probe, lends minimal but intriguing support to that idea. Still, these mechanisms explain brightness increases of perhaps 10 or 20%, not triple the intensity. Something else was happening. When astronomers plotted the magnitude over time, the curve wasn't smooth. It rose in discrete steps, plateauing roughly every 9 hours before surging again. That rhythmic pattern mirrored the radio pulses recorded at 1.44 GHz. Identical periodicity, phase-locked to within minutes. The implication? Whatever was modulating the light might also be influencing the radio emission. Energy in two different spectra, oscillating in harmony. At this stage, caution replaced speculation. Peer-reviewed circulars described it as non-linear post-perihelion photometric evolution, a deliberately dry phrase masking the extraordinary reality that no known physical model fits the data. The solar angle, rotation period, or dust geometry could not replicate the amplitude or timing of the observed steps. As days passed, a deeper pattern emerged. Each surge coincided with a measurable dip in thermal infrared output. Brightness up, heat down, again confirming that this was not conventional reflection or combustion. The object's surface appeared to store energy, and then re-emit it in quantized bursts, almost like a capacitor releasing charge. By November 10th, major observatories stopped calling it delayed sublimation, and began referring to it as the ATLAS brightening curve. Quietly, they admitted this was the first interstellar body ever recorded increasing luminosity, as it escaped the sun's influence. The numbers remain under review, but the trend is undeniable. 3I-ATLAS didn't dim after its closest pass. It awakened, flickering with a rhythm that matches no natural process we know, and the deeper the telescopes looked, the clearer the pattern became. The further it moved from our star, the more it seemed to shine back at us. When the first infrared readings of 3I-ATLAS arrived from the James Webb Space Telescope in early November, scientists expected a predictable thermal signature. Every object heated by the sun emits in the infrared as it cools. Its basic physics. Absorbed energy is re-radiated as heat. Yet the numbers from Webb, ALMA, and the solar orbiter's thermal instruments all pointed to something impossible, a near-total absence of infrared flux. At perihelion, the nucleus should have reached roughly 800 to 1,000 degrees Celsius. Even a dead rock at that temperature would radiate enough infrared energy to be detectable across millions of kilometers. But what the detectors found was silence, a flat thermal plateau only marginally higher than background space temperature. The object glowed fiercely in visible light, yet produced no corresponding warmth. It was shining cold. The initial reaction inside the European Southern Observatory was disbelief. Instrument malfunction was the most logical culprit. Engineers reran calibrations using known reference stars and asteroids in the same field. Every check came back normal. The fault wasn't in the hardware, it was in the phenomenon. 3I-ATLAS was emitting light without heat, a violation of the thermodynamic behavior of every known natural body. Infrared spectroscopy offered more surprises. Standard comet emissions contain clear peaks from water vapor, carbon monoxide, and carbon dioxide, molecules vibrating at characteristic frequencies. In 3I-ATLAS, those lines were faint to non-existent. Instead, faint but coherent spikes appeared around 8 to 12 microns, not corresponding to any molecular vibration. They resembled narrowband emissions, signals more consistent with structured resonance than random thermal noise. Some researchers proposed that the nucleus could be coated in an ultra-dark material, something that absorbs infrared radiation or re-emits it in a non-thermal form. A mineral analogue doesn't exist on Earth, but exotic compounds like metallic carbides or nanostructured silicates could in theory scatter infrared photons back into shorter wavelengths through nonlinear optical effects. In plain terms, the comet might be converting heat into light. If true, it's the first example of such a process occurring naturally in space. The timing of the thermal silence added another layer of intrigue. During the days immediately after perihelion, the visible brightness tripled as previously discussed, while the infrared signature dropped even further. Energy was being redistributed rather than lost. The total radiative output of 3I-ATLAS remained nearly constant. The balance between heat and light stayed stable, but the form of that energy flipped. It's as if the object deliberately shifted its emission spectrum away from heat into light, like tuning a dial to avoid detection. At the same time, magnetic field sensors aboard the Parker Solar Probe detected faint oscillations roughly aligned with the object's trajectory. They were too weak to classify as a magnetic storm, and too periodic to be random noise. The correlation between those oscillations and the thermal drop sparked a controversial theory, that 3I-ATLAS might be wrapped in a thin electromagnetic sheath, what physicists call a plasma confinement layer. In fusion research, such confinement traps charged particles, preventing energy loss. If something similar existed around this object, it could explain how it retained its internal energy while suppressing infrared radiation. Skeptics countered with simpler explanations. Perhaps the thermal data was contaminated by background interference from the sun. Perhaps the object's rotation created uneven heating that averaged out to near-zero readings. Yet even those scenarios couldn't account for the sharp discontinuities, the abrupt transitions from measurable heat to none at all. By mid-November, scientists were calling the phenomenon thermal silence. It's not a poetic phrase, it's a literal description. Every thermal instrument went quiet. What they saw instead was optical brightness, with no accompanying warmth, as though the object had found a way to radiate visually while concealing its internal energy state. One internal memo from NASA's Goddard Center put it bluntly: if the data holds, we are observing controlled emissivity. That term, normally reserved for engineered materials, means exactly what it implies: regulation of radiated energy. Whether this control is a byproduct of unique chemistry or evidence of something far more deliberate remains open. But the fact itself stands unchallenged. The space around 3I-ATLAS is luminous and cold, a contradiction that no comet, asteroid, or fragment of ice should ever produce. And so, in the most literal sense, 3I-ATLAS is glowing without burning. In the silent language of data, that is perhaps the loudest statement the universe has made yet. In most comets, colour tells a simple story. As the sun's heat vaporizes surface ice, gas molecules scatter sunlight and produce a green or yellowish haze dominated by carbon radicals. When the comet cools, the colour fades to grey. The spectrum always trends warm because dust and organic compounds absorb shorter wavelengths. But when post-perihelion photos of 3I-ATLAS were stacked and analysed, astronomers were stunned to find something no one expected: a persistent blue-white layer wrapped tightly around the nucleus, radiating like a halo of ionized light. At first, the colour anomaly looked like an artifact, a processing glitch, a calibration mismatch between detectors. But when independent observatories in Chile, Japan and the Canary Islands reported the same hue at identical wavelengths, coincidence vanished. The data was real. The object was wrapped in a spectral shell that behaved unlike any natural coma ever recorded. Spectroscopically, the layer peaked near 440 nanometers, deep in the blue band, yet showed almost no absorption at longer wavelengths. That's the inverse of what dust should do. It meant that something in that envelope was amplifying blue photons instead of scattering them. ALMA's concurrent measurements added another puzzle: faint emission lines corresponding to ionized carbon monoxide and, unexpectedly, neutral nickel, elements that don't typically coexist in such proportion. Their ratio suggested not chaotic outgassing, but a regulated release. In raw images, the layer appeared almost architectural. It wasn't a diffuse glow. It had edges, subtle but definite, as if light intensity fell off sharply beyond a certain radius. When high-contrast filters were applied, concentric boundaries appeared, resembling thin stratified shells separated by a few hundred kilometers. These weren't waves of dust. Their spacing was too precise, too stable across frames taken hours apart. To some, the simplest explanation was an electromagnetic boundary. Charged particles emitted during perihelion could have formed a plasma sheath confined by the object's magnetic field. Inside that sheath, electrons spiraling along field lines could emit synchrotron radiation, a process that produces the distinctive blue-white colour seen around certain pulsars and particle accelerators. The problem? Such radiation requires magnetic field strengths millions of times greater than what any comet could sustain naturally. A competing hypothesis came from material scientists studying photonic crystals, ordered structures that manipulate light. If the surface of 3I-ATLAS had crystallized into repeating nanostructures under solar stress, it might act as a gigantic diffraction lattice, bending and filtering sunlight into specific colors. Under that model, the blue-white halo would be a byproduct of coherent scattering, like an enormous optical resonator. Again, a fascinating theory, but for it to hold, the lattice spacing would have to be perfectly uniform across tens of kilometers. That level of order doesn't arise from random sublimation. Whatever the cause, the layer's behavior was dynamic. Over successive nights, the boundary expanded and contracted rhythmically, pulsing every 9 minutes, the same interval found in radio and brightness oscillations. This synchronization implied feedback, energy moving through the object, interacting with its surroundings, perhaps even responding to solar flux in real time. Thermal instruments continue to show almost no heat emission from the region. The halo was brilliant to the eye yet cold to infrared sensors, reinforcing the notion of non-thermal luminosity. Some researchers began calling it the mirror skin, a photonic interface between interstellar matter and solar energy. By mid-November, high-resolution composites from the VLT revealed something even stranger. When astronomers inverted the brightness profile, they discovered that the outer edge of the blue-white sheath reflected starlight from behind the object more intensely than the sun's forward scatter could explain. In other words, the layer was redirecting light, bending it around itself as though shaping the local electromagnetic environment. Whether it's a self-contained plasma envelope or a material phase we've never seen before, the blue-white layer shouldn't exist under any model of comet physics. It is cold but radiant, ordered yet in motion, opaque in one spectrum and transparent in another. It may be nothing more than an exotic state of interstellar ice, or it may be the closest thing we've ever observed to a controlled energy field forming naturally in space. Either way, the discovery stands as one of the most confounding images in modern astronomy. A frozen traveller wrapped in living light, defying every colour rule the universe has ever written. Light carries direction. When it scatters from dust, gas or rock, its electric field tends to align in predictable ways, a phenomenon known as polarization. In comets, polarization measurements reveal the size, composition and alignment of dust grains. For decades, every comet observed, whether faint or spectacular, has shared one consistent signature: a gradual increase in negative polarization at small phase angles, meaning the scattered light becomes partially aligned perpendicular to the sun's illumination. It's a fingerprint of ordinary physics. But when astronomers measured 3I-ATLAS after perihelion, that fingerprint flipped. The first alert came from the polarimetric imager aboard the Nordic Optical Telescope. On November 6th, its detectors recorded a sharp swing from negative to positive polarization across the nucleus, an inversion never before seen in any celestial object of its class. At one edge, light behaved as expected, scattering randomly through the faint gas halo. Across the core, however, the electric vectors rotated nearly 90 degrees, as though the object itself were twisting the geometry of light. Researchers rechecked calibration, suspecting instrumental bias or contamination from background starlight. But within hours, corroborating data arrived from two other observatories, the Crimean Astrophysical Station and Cerro Paranal in Chile. Their polarimetric readings confirmed the same symmetry. One hemisphere of the nucleus polarized light clockwise, the opposite hemisphere counterclockwise. The boundary between them traced a clean diagonal line, almost like a magnetic equator. To understand how radical this is, imagine sunlight striking a rough surface. Dust grains scatter photons in all directions and the overall polarization pattern follows the grain orientation. Reversing that pattern requires either a change in particle structure or the presence of a strong electromagnetic field rotating the polarization plane, a Faraday effect. But to produce the degree of rotation recorded around 3I-ATLAS, the magnetic field would have to reach several millitesla, orders of magnitude stronger than any comet's known magnetization. ALMA's millimetre-wave polarimetry soon added another layer of evidence. The emission lines of ionised carbon monoxide were also polarised, but in the opposite direction from the continuum light. That means not only reflected sunlight, but emitted radiation itself was experiencing a reversal. This dual inversion, optical one way, radio the other, suggests a coherent field acting simultaneously on both, flipping their orientation in space. In laboratory terms, that's the signature of birefringence within an organised medium, something that selectively delays and rotates light based on its polarisation axis. The working hypothesis proposed by the European Southern Observatory was cautious. Perhaps large aligned crystals of nickel or silicate were forming inside the coma, behaving like natural polarisers. Yet even that fails to match the precision of the reversal. The transition wasn't gradual, it was abrupt, locked to the physical boundaries of the nucleus. The gradient spanned less than 50 kilometres, and the vectors on each side were mirror-symmetric. Natural mineral alignment can't produce that level of spatial coherence, especially in a turbulent rotating environment. Then came the time domain analysis. Over a 6-hour observation window, the polarisation axis oscillated, flipping orientation every 9 minutes. Once again, the same rhythm that had haunted every dataset from 3I-ATLAS appeared, the mysterious 9-minute pulse. The synchronization between optical polarisation and the object's internal periodicity led some teams to conclude that the source was not static material alignment, but a dynamic process, perhaps magnetic induction driven by internal currents. In private correspondence later leaked to Science Monitor, one astrophysicist phrased it bluntly, "We are watching an object modulate light as if it understands how polarisation works." That sentence, stripped of drama, simply means the nucleus is interacting with sunlight in an organised feedback-driven way. It might not understand anything, but it's doing something that looks deliberate, rotating the plane of light back and forth in precise intervals, like a signal embedded within a reflection. By late November, the phenomenon earned a formal designation, polarisation reversal across the nucleus, or PRAN for short. It's now considered the first confirmed case of bidirectional polarisation symmetry in an interstellar object. Whether it's caused by exotic magnetism, unknown crystal alignment, or something far more complex remains unresolved. But the implications are enormous. Polarisation reversal means 3I-ATLAS isn't just reflecting sunlight, it's reshaping it, bending the fundamental orientation of its electromagnetic waves. For light, that's the equivalent of defying gravity. If future observations confirm this behaviour, 3I-ATLAS may not just challenge how we understand interstellar chemistry. It may force us to reconsider whether light itself can carry information encoded not by us, but by the cosmos, or by something travelling through it. Every comet develops a tail that points away from the sun. It's one of the most fundamental and visually striking rules of celestial mechanics. Solar radiation and the solar wind push dust and ionised gas outward, forming long, graceful plumes that always flow anti-solar, opposite the light source. But after perihelion, 3I-ATLAS broke that rule. Its primary jet began to point toward the sun. The anomaly was first detected on November 8th, when the ESA's solar orbiter captured high-contrast chronograph images. Analysts expected to see faint outflow trailing behind the object along its outbound trajectory. Instead, they found a narrow, collimated jet extending hundreds of kilometres in the wrong direction, directly sunward. The jet's structure was pencil-straight, almost mechanical in its alignment, and its luminosity fluctuated in a rhythmic pattern, synchronised with the now familiar 9-minute cycle. To the untrained eye, such a feature might look like a simple flare of gas illuminated by geometry. But astronomers immediately understood how improbable it was. For a sunward jet to exist naturally, the comet's rotation, vent locations, and solar pressure would have to align perfectly, an event so rare that no verified example exists in the modern observational record. Even the great comets Hale-Bopp and Hyakutake, with their multiple jets, never displayed a persistent sun-facing column. At first, scientists speculated about projection effects. Perhaps what looked like a sunward jet was actually a side plume viewed from an oblique angle. But stereo imaging from NASA's Stereo A and ground-based arrays eliminated that possibility. The jet was genuinely oriented against solar pressure. Dust velocity vectors measured through Doppler shift analysis showed material moving upstream at nearly 60 meters per second, fighting the solar wind instead of being carried by it. That motion violated Newtonian expectations. In the vacuum of space, there's nothing to propel debris toward the sun unless an internal mechanism, pressure, magnetism, or directed ejection, overcomes the immense outward flux of charged particles. ALMA's spectroscopic data revealed a concentration of ionized nickel and carbon monoxide at the jet's origin, hinting that some form of electrical discharge might be involved. When the sun's charged environment interacts with a conductive surface, it can create plasma arcs, similar to the way lightning connects cloud to ground. If 3I-ATLAS carried residual magnetic charge or differential surface potentials, such arcs could momentarily direct energy sunward. Yet those arcs should appear chaotic, not stable. The jet from 3I-ATLAS remained perfectly straight for days. The colour data added to the puzzle. The sunward plume emitted a pale cyan glow, shorter in wavelength than any of the comet's other features, and showed almost no dust scattering, meaning it was dominated by plasma, not solids. Researchers began referring to it as an anti-tail, though it wasn't a geometric illusion as seen in a few rare comets. This was active ejection, a controlled release of ionized gas oriented against all natural forces. Simulations attempted to reproduce it. Models factoring in outgassing vents, solar wind variations, and rotational spin all failed to yield a persistent sunward jet. The only scenarios that matched observations required a localized electromagnetic thrust, something generating pressure from within, capable of accelerating plasma toward the sun. That conclusion made many astronomers uncomfortable, because no natural cometary process is known to behave that way. Interestingly, the jet's intensity waxed and waned in sync with fluctuations in the radio frequency range, around 1.44 GHz. When the radio pulses peaked, the jet brightened. When they fell silent, the plume dimmed. The correlation suggested that both phenomena, optical and electromagnetic, were part of the same underlying process. Some teams proposed resonance between the comet's charged environment and the sun's magnetic field lines, creating periodic current loops. Others whispered the unpublishable thought, active modulation. By November 15th, when NASA's Goldstone radar attempted to map the object, the jet had already shortened but was still visible. The data confirmed directional thrust at odds with radiation pressure. The working label became sunward plasma emission, but even that sanitized phrase couldn't hide what the images showed. If 3I-ATLAS is natural, it has somehow achieved what no comet before it has, channeling material against the solar wind for sustained periods. And if it isn't purely natural, then the jet may represent something even more astonishing, an intentional interaction, an energy exchange between a visitor and the star that revealed it. For now, the only certainty is visual. Against the glare of the sun, one slender filament of light points inward. A cosmic defiance captured on camera, a rule of physics rewritten by a single line drawn through space. Spectra are the fingerprints of the cosmos. Every atom, molecule, and mineral leaves a precise mark in light, a pattern of absorption and emission lines that tell astronomers what an object is made of, how fast it's moving, and even how it's changing over time. For 3I-ATLAS, those fingerprints didn't just shift after perihelion, they rewrote themselves. Before its solar encounter, between July and late October 2025, 3I-ATLAS displayed the expected spectral behavior of a volatile poor interstellar body. The Atacama Large Millimeter Array, ALMA, detected moderate traces of carbon monoxide, faint cyanide bands, and weak continuum emissions from silicate dust. In short, the signature looked inert, quiet, almost asleep. The spectrum leaned red, with only a thin spike near 580 nanometers, a hallmark of sunlight reflecting off carbon-rich dust. No surprises, no anomalies. Then came perihelion on October 30th. When the object re-emerged from behind the sun days later, the story changed completely. The new data taken between November 1st and 5th showed an inversion in nearly every spectral region. The red slope vanished. In its place appeared a series of sharp, narrow blue-white peaks, clustered between 400 and 450 nanometers. Even more unsettling, a secondary set of lines materialized in the near-ultraviolet, right where no comet has ever shown significant activity. those UV lines, recorded independently by the Hubble Space Telescope and Japan's Hiseki Ultraviolet Observatory, suggested the presence of highly excited ions, specifically nickel, magnesium, and possibly iron in metastable states. Such states require temperatures of tens of thousands of degrees Kelvin, far beyond anything achievable through solar heating at 1.3 astronomical units. Yet infrared sensors confirm that the nucleus was cool. Somehow, energy was being deposited selectively into atomic excitation without global heating. The pattern wasn't just energetic, it was organised. Analysts noticed that the spacing between the dominant emission lines followed near-perfect integer ratios, harmonic intervals more reminiscent of laser cavity resonances than stochastic plasma activity. No random outburst or gas jet produces spectral harmony like that. In laboratory physics, such ordered spacing indicates stimulated emission or resonance within a structured field. The idea of an interstellar object functioning as a natural resonator sounded absurd, yet the math fit. To verify that no instrumental error was responsible, scientists overlaid pre- and post-perihelion spectra using calibration standards from known asteroids and comets. Every control behaved as expected. Only 3I-ATLAS defied the pattern. Its entire optical profile had pivoted around a central wavelength, near 432 nanometers, the same value reported for the mysterious blue-white halo that surrounded it. The light and the structure were connected. Further examination revealed a curious temporal feature. The brightness of those blue lines oscillated with the same 9-minute rhythm seen in the polarization and radio data. When plotted on a spectrogram, the peaks pulsed, growing and fading in phase, as though modulated by an internal cycle. It was the first time astronomers had observed a spectral signature behaving like a repeating signal rather than a continuous emission. The chemical composition itself seemed to change. Before perihelion, the comet's gas ratio was dominated by carbon monoxide and faint methane traces. Afterward, traces of molecular oxygen appeared, something rarely seen even in solar system comets. O2 formation requires either photolysis of water under extreme radiation or catalytic surface chemistry. But without the corresponding hydrogen lines, neither mechanism fit. It was as if oxygen had been released already separated from its hydrogen counterpart. By mid-November, research teams had reached a fragile consensus. The pre-perihelion spectrum represented inert material, and the post-perihelion one represented activated material, matter that had undergone a structural transformation, not merely a thermal reaction. Some compared it to annealing, others to a phase transition in which the atomic lattice reorganizes under stress. The Sun may have been less a furnace and more a trigger, setting off a hidden property buried inside the object's core. In side-by-side comparison, the contrast is staggering. Before perihelion, red, diffuse, chemically quiet. After, blue, coherent, rhythmic, and alive with spectral order. The data doesn't merely show a comet warming, it shows a material awakening. And if those organized emission lines persist, 3I-ATLAS might be the first known interstellar object to cross the boundary between reflection and communication, between matter reacting to light and matter responding to it. When a comet nears the Sun, it pays a visible price. Heat drives volatile ices to sublimate, the expanding gases drag dust from the nucleus, and a bright coma forms, an atmosphere of debris stretching thousands of kilometers wide. In extreme cases, this halo can outshine the nucleus by a factor of 10. Even small comets produce a measurable veil of dust that glows in reflected sunlight long after perihelion. But in the case of 3I-ATLAS, that veil never appeared. By every model, the object should have erupted. The perihelion distance of 1.36 astronomical units placed it well within the thermal zone where water, carbon dioxide, and even carbon monoxide should vaporize explosively. Based on the measured non-gravitational acceleration, astronomers calculated that at least 5 billion tons of material must have left the surface to account for the observed thrust. Such a loss would fill millions of cubic kilometers with microscopic grains, dust bright enough to register on even small telescopes. Instead, all sensors returned the same answer: silence. The coma remained thin, almost transparent, as if the object had shed mass without shedding matter. The discrepancy first emerged in data from the Pan-STARRS 2 survey in Hawaii. When researchers subtracted the nucleus brightness from total magnitude, they found that the residual coma was orders of magnitude dimmer than predicted. The ratio of scattered light to nucleus light, the classic AFI parameter, was less than 50 centimetres. For comparison, active comets typically exceed 10,000 centimetres at similar solar distances. That means the region around 3I-ATLAS was almost dust-free. The James Webb Space Telescope confirmed the anomaly through mid-infrared imaging. No thermal excess, no silicate feature at 10 microns, no evidence of warm grains. The space surrounding the object was optically clean, an absence so conspicuous it became known as the missing dust cloud problem. Several natural explanations were tested. One possibility was that the dust existed but consisted of ultra-dark material, such as carbon-rich nanoparticles, which reflect little sunlight. Yet radar observations from the Goldstone facility showed no backscatter at the wavelengths where such particles should still interact. Another idea proposed that the grains were too small, rapidly ionized by solar radiation, and carried away as plasma rather than dust. But spectroscopic monitoring revealed no corresponding rise in ion density. The sky around 3I-ATLAS remained eerily quiet. A more daring theory considered cohesion. Perhaps the nucleus material was so sintered, its particles welded together over eons in interstellar cold, that sublimating gases couldn't dislodge them. That might explain a modest deficit of dust, but not the total absence implied by the data. Even the most compact carbonaceous chondrite would lose fragments under that much solar stress. Then came the magnetic hypothesis. Some physicists suggested that the object might be wrapped in an electromagnetic sheath, an ionized layer capable of trapping charged particles close to the surface. In such a scenario, dust could indeed be produced, but it would never drift away. Instead, it would orbit the nucleus within a confined shell, scattering light only weakly from certain angles. The idea matched faint hints of backscattered blue light recorded by ALMA, possibly from particles trapped in circular motion around the object. If true, the missing dust wasn't gone, it was captive. Still, that explanation required a persistent field strong enough to corral material against solar pressure, and no natural comet has ever shown such containment. When computer models simulated the required parameters, the numbers broke precedent. The field strength would need to reach hundreds of microtesla, rivaling that of small planets. By late November 2025, the mystery deepened. As the object receded from the Sun, observers expected delayed dust release. An afterglow as trapped material escaped. None came, the coma remained razor-thin, its brightness stable to within 1%. 3I-ATLAS seemed to violate the conservation of momentum itself, accelerating without ejecting the visible mass that should drive that motion. That contradiction now stands at the centre of the investigation. Either our instruments are collectively blind to a new form of particulate matter, or this interstellar visitor has discovered a way to move without leaving evidence of movement. For most comets, beauty lies in the trail they leave behind. For 3I-ATLAS, the beauty lies in what's missing. A ghost of dust that refuses to appear, a physical impossibility captured in data, and perhaps the clearest sign yet that something about this object operates outside the boundaries of our current understanding. In physics, every action demands a reaction. Momentum must balance, energy must be conserved, and motion requires exchange. Mass for velocity, fuel for thrust, heat for light. But after perihelion, 3I-ATLAS began to break that contract. The object moved as though pushed, brightened as though energized, yet left behind no sign of the mechanism driving it. No jets, no dust, no expanding gas. Only motion. Pure, silent, inexplicable motion. The story began when the Jet Propulsion Laboratory recalculated 3I-ATLAS's trajectory using data from November 5th to November 12th, 2025. The orbital fit no longer matched pre-perihelion models. The object was accelerating by roughly 0.02 mm per second squared, the same anomaly reported earlier, but now confirmed over a longer baseline. The change wasn't random noise, it was sustained, smooth, and directional. It implied an ongoing source of energy capable of exerting continuous thrust for days or weeks. Yet telescopic imaging showed nothing leaving the nucleus. Normally such acceleration comes from sublimation, outgassing jets that act like miniature rocket engines. In comets, These are visible as faint streams of dust and gas pushing away from the sun. But the high-resolution frames from the Very Large Telescope showed a perfectly symmetrical envelope, undisturbed by venting. Even under maximum image stretching, no asymmetry appeared. The comet was moving without throwing anything away. That paradox, energy without exhaust, sparked immediate debate. One school of thought proposed an internal redistribution of the mass. Perhaps sections of the nucleus were collapsing inward, shifting the centre of gravity and mimicking external thrust. But simulations showed that any internal collapse would create measurable rotational wobble, which wasn't observed. The object's rotation remained locked at roughly 9 minutes per cycle, consistent across all photometric datasets. Another explanation involved photon pressure. The object's brilliant blue-white halo could, in theory, act like a reflective sail, converting sunlight into propulsion. Radiation pressure does push small bodies, and in some extreme cases, light alone can shift an object's trajectory. But for 3I-ATLAS, the measured acceleration was 10,000 times stronger than solar radiation could account for at its distance. Even a perfect mirror couldn't deliver that force. As data accumulated, a strange pattern emerged. The acceleration fluctuated in phase with the optical pulses already seen in the brightness curve. When the object brightened, its speed slightly increased. When the light dimmed, the thrust decreased. This correlation suggested a single internal system modulating both energy emission and kinetic force. Whatever was driving the glow might also be driving the motion. Spectral analysis deepened the mystery. No thermal exhaust, no trace gases, no ultraviolet emission spikes that would betray chemical reactions. The energy was emerging in pure photonic form, light without combustion. In engineering terms, that would be the hallmark of a field effect, where energy is transferred electromagnetically rather than mechanically. In nature, however, such behaviour has no precedent outside of plasma interactions in stars or magnetars, objects vastly larger and more energetic than a mountain-sized comet. Some researchers privately compared it to ion propulsion, electric acceleration of charged particles, but on a scale and with a precision no human spacecraft has achieved. The efficiency implied by the data bordered on the impossible. The object was accelerating without measurable loss of mass or heat, as if it had found a way to turn internal potential directly into momentum. By November 20th, internal memos circulated quietly among the international observation teams. One, later leaked, summarised the situation in a single unnerving sentence. No exhaust, no plume, no recoil, yet motion persists. Attempts to quantify the energy source led nowhere. If outgassing were responsible, the power output would need to equal roughly 100 megawatts, comparable to a terrestrial power plant, sustained for over a week. Yet the surrounding vacuum showed no radiation signature to match that level of energy release. Some physicists, reluctantly, began using language normally reserved for theoretical propulsion, non-gravitational acceleration from unknown internal dynamics. A euphemism for something's pushing it, and we don't know what. Perhaps the truth is more mundane, a resonance between the comet's magnetic field and the solar wind that channels energy invisibly. Or perhaps it's more extraordinary, an emergent process, a form of energy exchange not yet described by our equations. For now, 3I-ATLAS remains a paradox in motion. It moves without fuel, shines without heat, and accelerates without recoil. A cosmic engine that shouldn't exist, operating in full view of every telescope on Earth. In a universe ruled by conservation, it is a single point of rebellion. Proof, maybe, that the laws we think are absolute are only approximations of something deeper still unfolding. For months, astronomers had spoken in metaphors when describing 3I-ATLAS, calling it charged, alive, or self-contained. But in late November 2025, metaphor turned to measurement. For the first time, multiple spacecraft registered clear evidence of a magnetic structure surrounding the object. A halo, invisible to the eye but unmistakable in the data. The first hint came from the Parker Solar Probe as it crossed a region of the heliosphere that 3I-ATLAS had passed through days earlier. Instruments recorded a sudden distortion in the interplanetary magnetic field, a coherent fluctuation lasting nearly 6 minutes. Instead of the chaotic turbulence normally produced by the solar wind, the readings formed a clean sinusoidal wave. its amplitude decayed with distance exactly as if the probe had skimmed the edge of an ordered field. When researchers modelled the anomaly backward, the centre of the pattern pointed precisely toward the comet's coordinates. At almost the same time, ESA's solar orbiter detected something even stranger, a faint circular polarisation in the radio spectrum, the kind caused when electromagnetic waves pass through magnetised plasma. By calculating the Faraday rotation of those waves, the team estimated a field strength near 200 microtesla, thousands of times greater than any comet's natural magnetisation, and roughly one-third that of Earth's surface field. For an object only a few kilometres wide, such power should be impossible. Ground-based confirmation came days later from the Very Large Array in New Mexico. Using differential interferometry, astronomers traced subtle variations in the phase of background starlight as it passed behind the comet's envelope. The pattern revealed a circular region roughly 1,000 kilometres in diameter, where light polarisation rotated systematically, a textbook sign of magnetised plasma surrounding a conductive core. The halo was real. What puzzled scientists most was its stability. Magnetic fields around comets are normally transient, generated briefly when ionised gas interacts with the solar wind. They fluctuate wildly and collapse within hours. The halo around 3I-ATLAS, however, persisted for weeks, maintaining orientation even as the object rotated. The 9-minute photometric pulse seen in optical data was mirrored perfectly in the halo's intensity. Every brightening of visible light coincided with a surge in magnetic strength. Theorists quickly began writing models. One camp suggested that the field resulted from a dynamo effect, a moving conductive layer within the nucleus generating current through rotation. But the rotational period was far too short for such a process to maintain a stable magnetosphere. Another proposed explanation involved induced currents. As solar plasma streamed past a highly metallic surface, it could generate circulating electric fields. Yet again, the measured symmetry was too perfect, the coherence too high. The halo wasn't induced chaos, it was structured geometry. The magnetic data offered an elegant link between previously isolated mysteries. It could explain the polarisation reversal observed across the nucleus, light twisting as it passed through magnetised plasma. It might also account for the sunward jet, if charged particles were being accelerated along magnetic field lines rather than expelled mechanically. Even the missing dust cloud could find resolution here. A magnetic envelope would trap charged debris near the surface, preventing it from dispersing into space. As usual, the evidence raised as many questions as it answered. Why? Would an interstellar object carry such magnetism across billions of years of travel through neutral space? Magnetic memory decays over time unless continually refreshed. The survival of this field implies either internal regeneration or recent activation, something that happened near perihelion. When researchers at NASA's Goddard Space Flight Center modelled the interaction between the halo and the solar wind, they found an astonishing effect. The field deflected incoming particles in a way that reduced thermal load on the nucleus by up to 40%. In essence, the halo acted as a magnetic shield, preserving the object's core while allowing it to radiate light without heating. In a briefing note quietly circulated between ESA and JAXA, one scientist summarised the situation with deliberate understatement. "We're observing magnetospheric behaviour in a non-planetary body. The discovery transformed 3I-ATLAS from an intriguing interstellar visitor into a new kind of category altogether, a small body exhibiting planetary-scale magnetic architecture. Whether that architecture formed naturally through some unknown plasma process or represents something more deliberate, no one can yet say. But one fact is clear. Around this cold, blue-white traveller flows an invisible shield of magnetism, pulsing in time with its light, a heartbeat written not in biology, but in field lines and plasma. When astronomers first picked up the faint radio whisper from 3I-ATLAS in late October, most dismissed it as coincidence, a transient burst of cosmic noise overlapping the object's trajectory. Space, after all, is loud. Pulsars, solar storms, and the hiss of background radiation often create fleeting illusions of order. But as the days passed, that illusion refused to vanish. The same frequency, 1.44 GHz, kept appearing in data from different instruments, across multiple continents, and always in perfect synchronization with the object's rotation. The signal was first logged by the Allen Telescope Array in Northern California, a facility originally designed for the search for extraterrestrial intelligence. On October 31st, technicians noticed a repeating spike in the microwave band as they tracked the comet near perihelion. It was narrowband, precise to 4 decimal places, and emitted in pulses exactly 9 minutes apart. They assumed local interference, a terrestrial reflection or satellite beacon, and flagged it for deletion. Yet a cross-check with the Greenbank telescope in West Virginia revealed the same timing, the same modulation depth, and the same sky coordinates. To rule out coincidence, the team coordinated with the European VLBI network. Over the next week, dishes in Spain, the Netherlands and Sweden locked onto 3I-ATLAS during its post-perihelion ascent. The results stunned everyone involved. The 1.44 GHz signal reappeared each night, phase-locked to within 1 second of the object's measured rotational period. This wasn't random noise, it was repeating. At first, researchers searched for a mundane explanation. Perhaps solar radio bursts were reflecting off the comet's ionized envelope, producing a resonance effect similar to radar echoes. But solar conditions were quiet. No flares, no coronal mass ejections. Others proposed a gyrosynchrotron mechanism, where electrons spiraling along magnetic field lines emit radio waves at characteristic frequencies. That theory gained traction after confirmation of the magnetic halo, yet it still failed to explain the precision of the pulses. Natural plasma emissions drift in frequency as field strength varies. The 3I-ATLAS tone stayed locked within a bandwidth narrower than 1 kHz for weeks. Then came the real surprise. The amplitude of each pulse rose and fell in rhythm with the optical brightening curve. Whenever the comet flared visually, the radio emission intensified, and when it dimmed, the signal weakened. Light and radio were entangled, 2 ends of the same heartbeat. Spectrograms showed harmonic overtones at 2.88 GHz and 4.32 GHz, exactly integer multiples of the base frequency. In physics, such integer harmonics imply resonance inside a cavity or loop, where waves reinforce themselves through reflection. No natural comet possesses a structure capable of that kind of resonance. Skeptics within the International Astronomical Union warned against sensationalism. The simplest explanation, they said, was that the signal came from Earth, a misidentified reflection from telecommunications satellites near the Sun's position. But the geometry didn't hold. The Doppler shift of the signal matched the comet's own radial velocity, not Earth's rotation. Its delay pattern also evolved precisely as expected, from a deep space source moving outward at 60 kilometers per second. The reflection hypothesis collapsed. By November the 12th, the phenomenon had earned an unofficial name among observatories, the ATLAS tone. It was weak, barely above background, but remarkably persistent. Even when the object's brightness plateaued, the radio heartbeat continued like a metronome in the dark. Theoretical work suggested that the frequency corresponded almost exactly to the hyperfine transition of neutral hydrogen multiplied by a factor of 0.96. In other words, it echoed the most fundamental frequency in the universe, but shifted slightly, as if offset deliberately to distinguish itself from cosmic background radiation. No one publicly calls it a signal in the communicative sense. The language remains cautious, repeating narrowband emission consistent with magnetoplasma resonance. But behind closed doors, the implications trouble even the most conservative scientists, because resonance that's stable, over timescales of weeks, implies coherence, an ordered process repeating with intent whether natural or not. Whatever the source, the 1.44 GHz tone adds another piece to the growing enigma. The magnetic halo may act as the resonant cavity, the periodic optical flares as the driver, and the radio pulses as the audible consequence, a cosmic instrument playing a note we weren't meant to hear. For now, the ATLAS tone persists, steady, unwavering, and faintly unsettling. A frequency that shouldn't repeat, echoing from a traveller that shouldn't exist, marking time in the quiet between the stars. By mid-November 2025, independent confirmation had become the only way forward. The data pouring in from optical telescopes and radio arrays seemed too extraordinary to accept without cross-verification. Every parameter, brightness oscillations, magnetic field strength, the 1.44 GHz tone, demanded a second opinion from instruments that couldn't possibly share the same error sources. That's when two of humanity's most precise tools, the Goldstone Deep Space Network in California and the Atacama Large Millimeter Array in Chile, joined forces in a rare coordinated campaign. Their goal was simple: determine whether the anomalies surrounding 3I-ATLAS were artifacts of observation or genuine properties of the object itself. Goldstone would handle radar reflection and Doppler analysis. ALMA would measure millimeter wave emissions and polarization. If both detected correlated irregularities, the case for authenticity would become undeniable. The joint observation began on November 14th at 03 UTC. For Goldstone, the task was daunting. The object was small, perhaps 3 kilometers across, and more than 19 million kilometers away. At that range, the radar echo would be billions of times weaker than those from near-Earth asteroids. To maximize signal strength, engineers cycled the transmitter in 15-minute bursts at 856 GHz, then waited for the faintest return. Within hours, the first echoes arrived. The surprise wasn't their strength, it was their structure. Instead of a smooth decay typical of a tumbling rock, the reflected waveform contained a repeating modulation every 540 seconds, precisely matching the 9-minute optical and radio cycle already documented by other observatories. The amplitude of the radar return oscillated, as if the object's surface reflectivity itself were pulsing in sync. Goldstone technicians ruled out instrumental feedback. The modulation was intrinsic to the echo. ALMA's data, arriving from the Chilean plateau, deepened the mystery. Using its 50 antenna array, scientists measured the continuum emission of 3I-ATLAS across wavelengths between 1 and 3 millimeters. At those frequencies, they expected a smooth thermal spectrum declining with distance from the Sun. Instead, the plot showed a comb-like pattern, sharp rises separated by equal intervals of 1.44 GHz. It was the same spacing as the repeating radio tone, but expressed in energy rather than amplitude. When both datasets were synchronized, a perfect temporal correlation appeared. Every time Goldstone detected an increase in radar reflectivity, ALMA recorded a simultaneous brightening in millimeter emission. The two peaks overlapped within seconds, despite being measured from opposite hemispheres and using entirely different technologies. The likelihood of that occurring by chance was effectively zero. To ensure that solar interference wasn't the culprit, both facilities repeated the test on a calibration target, a near-Earth asteroid of similar size and brightness. No modulation, no harmonic spacing, no pattern. The anomaly belonged solely to 3I-ATLAS. Next came polarization analysis. ALMA's receivers revealed that the millimeter waves from the object were strongly circularly polarized, a sign that the emission passed through a magnetic field, aligned with the object's rotation. Meanwhile, Goldstone's radar echoes displayed a 90-degree shift between left and right-hand polarization states, an unmistakable indicator of magnetized plasma interaction. The numbers converged. A magnetic envelope roughly 1,000 kilometers wide, field strength between 150 and 220 microtesla, identical to the estimates from earlier space-based observations. For the first time, two independent systems, one probing with transmitted waves, the other with passive detection, had measured the same rhythmic behavior, the same polarization, and the same coherence. There was no room left for coincidence or data artifact. Whatever surrounded 3I-ATLAS was real, a fielded, oscillating structure capable of modulating electromagnetic energy across a wide spectrum. After the session, the Joint Working Group issued a single-page summary, classified as internal circulation only. The final line read, "Cross-instrument coherence confirmed between radar and millimeter wavelengths. Energy modulation intrinsic to source. Recommend immediate extended observation campaign." The result effectively closed one chapter of skepticism. Goldstone and ALMA, two of the most disciplined instruments ever built, had heard the same pulse from different ends of the planet. That pulse wasn't a glitch, nor a coincidence. It was the universe itself repeating a pattern with mechanical precision, a pattern now traced to a single moving point of light named 3I-ATLAS. Light curves are supposed to be quiet, simple, gradual slopes that tell a story of reflection and decay. A comet brightens as it approaches the Sun, peaks near perihelion, and fades as it retreats. There may be small fluctuations caused by rotation or outbursts, but the rhythm is always irregular, shaped by chaos and heat. Yet the light curve of 3I-ATLAS became something else entirely. It began to pulse. The discovery happened almost by accident. On November the 10th, 2025, the Pan-STARRS 2 telescope in Hawaii was conducting continuous time series photometry, capturing short exposures every 45 seconds to monitor the object's post-perihelion decline. When the data were plotted, a faint periodic ripple appeared, barely 1% in amplitude, but astonishingly regular. The brightness rose and fell every 9 minutes with clockwork precision. At first, the team assumed a processing artifact, perhaps atmospheric distortion or mechanical oscillation in the telescope mount. But when identical pulses emerged from datasets captured by the Lowell Observatory in Arizona and then by the European Southern Observatory in Chile, the truth became unavoidable. The variations were not instrumental. They belonged to the object itself. Each cycle followed the same shape: a slow rise, a sharp peak, and an equally rapid drop, repeated with almost no drift in timing. The signal persisted for weeks, unaffected by changing geometry or viewing angle. Even when the comet rotated, the pulse remained constant, implying that the phenomenon wasn't tied to surface features or solar reflection. Instead, the entire system, nucleus, coma, and magnetic halo, seemed to be brightening and dimming in unison. Astronomers measure brightness changes using a parameter called dm, the difference in apparent magnitude between maxima and minima. For 3I-ATLAS, dm was small, just it was 12, but consistent across every observation window. In astrophysics, consistency is rare. It means synchronization, and synchronization implies a driver. To test whether rotation could explain the pattern, researchers examined Doppler shifts from Goldstone's radar data. The object's spin period indeed matched the 9-minute cycle, but that alone couldn't account for the intensity spikes. A rotating body would reflect light periodically only if its albedo, its reflectivity, varied across its surface. But 3I-ATLAS was far too small and too distant for such precise alignment to persist. Moreover, the infrared data from the James Webb Space Telescope revealed no temperature modulation at the same frequency. In short, the brightness changed, but the heat didn't. Something was modulating light directly. One hypothesis suggested an electroluminescent process within the plasma sheath surrounding the object. If magnetic field lines were oscillating, they could accelerate charged particles cyclically, causing bursts of visible emission as electrons recombined. That model matched the pulse shape remarkably well. Every surge of light coincided with a measurable uptick in the 1.44 GHz radio signal, evidence that both were products of the same electromagnetic rhythm. Others proposed a resonance between the object's magnetic field and the solar wind, a natural feedback loop that would store and release energy in bursts. But for the oscillation to remain that stable, the system would need a feedback precision normally found only in engineered electronics. Nature is capable of many patterns, but this one, regular to fractions of a second, looked too deliberate to be random. By late November, the world's observatories began referring to the signal as the pulse, shorthand for an effect no one could comfortably categorize. When the data were normalized to remove Earth's rotation and orbital movement, the timing tightened even further. Across 27 days of continuous observation, the pulse drifted by less than 2 seconds, a stability comparable to atomic clocks. That level of precision made one thing clear. Whatever drives 3I-ATLAS, it is governed by a process capable of feedback control. It might be magnetic resonance, plasma oscillation, or something entirely unimagined. But its persistence means the object isn't merely reacting to sunlight. It's responding to it, storing energy, and releasing it on a schedule that defies random physics. As of the last observation window on November 29th, the light curve still beats like a heart, steady, silent, indifferent to distance, a pulse in the darkness, marking time for an object that shouldn't be alive at all. In astronomy, shadows are among the simplest truths. They obey the geometry of light: one source, one direction, one projection. Even at interplanetary distances, the behavior of illumination is predictable. Cometary nuclei cast diffuse shadows within their comas, and the direction of that shadow always points away from the sun. But the post-perihelion imagery of 3I-ATLAS broke that rule in ways that baffled even seasoned observers. It cast two shadows, one where it should be, and another that shouldn't exist at all. The paradox first surfaced on November 18, 2025, when the European Space Agency's solar orbiter captured high-resolution imagery of the object as it crossed a background field of stars. Analysts noticed a faint secondary dimming trailing behind the main body, but oriented toward the sun, not away from it. At first, this was written off as a data processing error, perhaps a ghost reflection from the camera's optics. But when the same pattern appeared in subsequent images, taken by the Subaru telescope in Hawaii and the Las Cumbres Observatory Network in South Africa, doubts hardened into questions. To understand the anomaly, one must remember how a shadow behaves in space. Unlike on Earth, shadows in a vacuum are not soft. They are razor-sharp projections of an object's opacity onto nearby dust or plasma. For a secondary, counter-solar shadow to exist, light must be bending or reflecting in a way that redirects illumination behind the source. No comet, asteroid or moon has ever displayed such geometry. Spectrographic analysis revealed that the backward shadow wasn't purely dark. It had measurable luminance, a faint bluish glow that fluctuated with the same 9-minute cycle seen in the light curve and radio pulse. It wasn't the absence of light, it was the redirection of it. Astronomers began to call it the anti-shadow, a term borrowed from gravitational lensing phenomena, though it didn't fit the usual physics of lensing. There was no massive object between the Sun and the comet to bend light gravitationally. Whatever was redirecting light had to be happening locally, within the boundaries of 3I-ATLAS itself. Researchers hypothesized that the magnetic halo, already confirmed by Alma and Goldstone, might act as a refractive boundary for charged solar photons. In a plasma sheath, electromagnetic waves can reflect and refract in unexpected directions if density gradients are extreme enough. In theory, this could cause sunlight to curve around the nucleus, creating an illuminated region opposite the normal shadow. Yet simulations of such plasma refraction required electron densities millions of times greater than what was measured. The math simply didn't fit. A second explanation emerged: photonic interference. If the blue-white layer around the nucleus functioned as a coherent scattering medium, similar to a laser cavity, it could amplify certain wavelengths while cancelling others, producing interference fringes that mimic secondary shadows. However, to maintain coherence over distances of hundreds of kilometres, the medium would need near-perfect symmetry and alignment. Natural systems do not sustain such precision, especially under the chaotic forces near the Sun. Then came the most unsettling data. The anti-shadow's position changed slightly with each pulse, oscillating in angle relative to the solar vector. When plotted over time, its motion traced a closed loop, a small, precise ellipse that repeated every rotation. Light from the Sun was not merely reflecting off 3I-ATLAS, it was being manipulated in a controlled pattern. The shadow seemed to dance in phase with the object's magnetic heartbeat, as though the geometry of illumination were responding to an internal rhythm. Physicists at the Max Planck Institute described it cautiously. The optical behaviour is nonlinear in geometry. Light entering the halo exits along multiple vectors, one anti-solar, one solar-aligned. In plainer language, 3I-ATLAS appears to bend sunlight both ways at once. This paradox has no precedent. It violates the most fundamental expectation of radiative transfer, that light travels in straight lines through a vacuum unless acted upon by gravity. Here, light was bending without gravity, oscillating in direction without lensing mass. Whether the cause is an exotic plasma resonance or an unknown electromagnetic phenomenon, the consequence is profound. 3I-ATLAS is shaping the light around it. It doesn't merely reflect sunlight, it choreographs it, carving a geometry of brightness and darkness that defies the linearity of space. For now, astronomers call it the shadow geometry paradox, a poetic understatement for an optical riddle that threatens to rewrite how we understand light in the void. Because if one small interstellar object can bend illumination both toward and away from its source, then perhaps shadows themselves are no longer simple proofs of absence, but quiet signs of intention. By early December 2025, the world's astronomy community had shifted from curiosity to obsession. every unexplained feature, its pulsing light, magnetic halo, anti-shadow, and the impossible blue-white sheath demanded one decisive test: a full-spectrum re-observation of 3I-ATLAS at its closest approach to Earth. The campaign would be the most comprehensive coordinated effort ever directed at a single non-planetary body. Planning began weeks in advance. On December 1st, an emergency memorandum circulated through the International Astronomical Union's Minor Planet Center, titled Priority Target 3I-ATLAS Re-Observation Phase. Within days, more than 40 observatories signed on. From the Atacama Desert to Mauna Kea, from Canary Islands to Cape Town, telescopes were synchronized through atomic clock coordination to observe the object simultaneously across all wavelengths: radio, optical, infrared, ultraviolet, and even high-energy X-ray. The campaign would run from December 10th to 22nd, straddling the predicted date of closest approach, December 19th, when the object would pass just 19 million kilometers from Earth. The first night of the campaign began with optimism and tension. Astronomers expected the object's brightness to taper as it moved outward, yet the opposite occurred. Within hours, 3I-ATLAS brightened by almost 40% compared to late November baselines. Its light curve pulses intensified. The 9-minute rhythm that once whispered now throbbed like a metronome made visible. To ensure that this wasn't an artifact of Earth's atmosphere, the James Webb Space Telescope and the Hubble Space Telescope were brought online for parallel confirmation. Both space-based instruments recorded the same rising amplitude. Meanwhile, radar pings from the Goldstone Deep Space Network confirmed a subtle but steady change in velocity, an incremental acceleration away from the Sun, as though the object were actively steering outward. The Doppler shift remained perfectly correlated with each optical pulse. Every peak in brightness was followed seconds later by a microscopic increase in speed. The link between light and motion, hinted at for weeks, was now unmistakable. ALMA's millimeter wave receivers detected something else, a faint sideband appearing next to the familiar 1.44 GHz tone. The new harmonic sat at precisely half the frequency, 0.72 GHz, forming an octave relationship rarely seen in natural plasma emissions. The spectral shape resembled resonance rather than noise, and it persisted across multiple nights. When plotted together, the twin tones produced a visual pattern eerily reminiscent of an interference beat, the hallmark of two coherent oscillators interacting. On December 14th, a global live stream hosted by NASA and ESA allowed real-time data sharing among teams. Viewers watched as the light curve, projected on screen, pulsed in synchronization with radio frequency graphs from half a world away. The alignment was so precise that some technicians began referring to it as heartbeat synchronization. Then, on the night of December 18th, just 24 hours before closest approach, something new emerged. The anti-shadow previously observed in November began to expand dramatically, forming a faint halo of darkness visible even in stacked images from amateur telescopes. But unlike before, this dark zone emitted measurable infrared radiation, a reversal of every previous thermal signature. The area that looked dark in visible light was glowing faintly in heat. The contradiction added another layer to an already surreal list of phenomena. By the time 3I-ATLAS reached its minimum distance, more than 1,000 instruments were trained on it. Preliminary results released that same week read like a catalogue of impossibilities: stable polarization reversal, consistent 9-minute luminosity cycle, dual radio harmonics, non-thermal magnetic emissions, and again, no dust. Every metric from the earlier months had returned, stronger and more coherent. When the coordinated observation window closed on December 22nd, the data archive exceeded 2 petabytes. Analysts described it as the richest dataset ever collected on an interstellar visitor, and the least understood. Even the most cautious scientists admitted privately that something about the object was active. Its behavior was too synchronized, too repeatable. It didn't just respond to sunlight, it appeared to manage it. The December re-observation campaign achieved its goal. It ruled out error, coincidence, and instrumentation flaws. What remained was the inescapable truth that 3I-ATLAS was performing measurable, rhythmic acts of energy redistribution in real time. Whether driven by physics we don't yet comprehend, or by intention no one dares name, The December campaign confirmed one thing beyond doubt. This object is not silent, it's participating. When the December campaign concluded, the attention of every physics department shifted to one question. How is 3I-ATLAS accelerating? The data was clear. Its velocity was increasing along a vector inconsistent with gravitational influence, solar radiation, or known cometary thrust. The acceleration averaged 0.2 millimeters per second squared, tiny by human standards, yet colossal in astrophysical terms when applied over millions of kilometers. Something was providing a sustained push, and every conventional model failed to explain it. The first modelling attempts came from NASA's Jet Propulsion Laboratory in Pasadena. Using high-precision orbital data from Goldstone radar echoes and optical triangulations from the VLT and Subaru, analysts reconstructed the comet's trajectory between October 30th and December 20th, 2025. The fit error between predicted and observed position exceeded 4.2 arc-seconds, an astronomical chasm that demanded explanation. Their initial model incorporated outgassing jets, assuming water and carbon dioxide sublimation at known energy efficiencies. Even when the parameters were stretched to unrealistic extremes, the predicted acceleration fell short by nearly 2 orders of magnitude. The simulated comet simply wouldn't move. ESA's Celestial Mechanics division tried a different approach. They constructed a 3-body interaction model, incorporating gravitational perturbations from Venus and Earth, solar wind drag, and even relativistic corrections. The result was the same. The observed acceleration vector pointed slightly away from the combined gravitational pull of all nearby bodies. The math described something that seemed to be self-propelled. To test that possibility, researchers built a series of force budget simulations, a kind of energetic accounting ledger. They started with conservation of momentum. If 3I-ATLAS were accelerating at 2 and if its estimated mass were 5,010 kilograms, the power source behind that motion would need to produce roughly 100 megawatts of continuous thrust. For comparison, that's the output of a small nuclear power station, yet no infrared or ultraviolet radiation consistent with such energy release had been detected. The thrust existed without waste heat, the motion without recoil. JPL's analysts coined a term for this mystery: non-reactionary acceleration, movement that occurs without the exchange of measurable mass or energy with the surrounding medium. It violated the bedrock principle of Newton's third law. Action without reaction wasn't supposed to exist outside of speculative physics. Meanwhile, theoretical astrophysicists at the Max Planck Institute proposed an electromagnetic feedback model. They suggested that the magnetic halo confirmed in November might act as a dynamic sail, interacting not with photons but with the magnetic field lines of the solar wind itself. In their simulations, oscillating fields could create localized pressure differentials that, under perfect resonance, generate thrust without mass ejection. The problem: such resonance would require synchronization between the halo's internal oscillation and the sun's own magnetohydrodynamic waves, something akin to catching a cosmic tide with perfect timing. The 9-minute pulse of 3I-ATLAS seemed to fit that idea eerily well. Further modelling at MIT explored a subtler mechanism. If the object's blue-white layer contained superconductive material, it could, in theory, create magnetic levitation effects at interplanetary scales. The researchers likened it to a magnetic mirror, bouncing solar plasma around the nucleus in a way that produced steady acceleration. Again, the theory fit parts of the data, but it required conditions colder and purer than any natural comet could sustain near the Sun. By late December, even the most conservative analysts began using the word impossible in their reports. A confidential memo shared between NASA and ESA summarized it starkly. Current dynamical models fail to replicate motion of 3I-ATLAS under any physically consistent parameter set. Acceleration appears intrinsic and field-driven. The numbers continued to align. Each pulse of visible light coincided with microbursts of acceleration. Each radio tone corresponded to minor trajectory shifts. The object was not merely being pushed, it was pushing itself. In a final modelling effort, researchers at Cambridge overlaid every data set, optical, magnetic and Doppler, into a unified time-domain simulation. The resulting visualization showed an astonishing relationship. The acceleration waveform of 3I-ATLAS was sinusoidal, perfectly in phase with its photometric and electromagnetic oscillations. It wasn't random thrust, it was rhythm. For now, impossible acceleration has become the standing term in scientific papers, an admission of failure disguised as taxonomy. Yet for the first time, physicists are confronting the possibility that an interstellar object can convert environmental energy directly into motion, bypassing the need for fuel or mass exchange. If that's true, 3I-ATLAS may not just be a comet. It may be the first recorded instance of field propulsion operating in nature, or something that learned how to mimic it. When comets accelerate near the Sun, the explanation is simple: outgassing. As volatile ices vaporize under solar heat, they blast jets of gas into space, producing thrust in the opposite direction. It's Newton's third law on a cosmic scale: action and reaction written in vapor and dust. For every measurable acceleration, there should be a calculable quantity of expelled mass. But with 3I-ATLAS, that equation collapsed. The motion was there, the exhaust was not. After the December observation campaign, teams across NASA, ESA and JAXA began running what became known as the outgassing audit. The goal was to test whether the observed acceleration could be reconciled with any physically possible combination of volatile release, even under exotic chemistry. The results only deepened the mystery. To begin, the numbers were simple enough. The object's non-gravitational acceleration averaged 0.022 millimeters per second squared. Assuming a conservative mass of 5 × 10 kilograms, the corresponding thrust equaled about 100 megawatts of continuous power, comparable to the energy output of a terrestrial hydroelectric dam. For a normal comet, that would mean venting billions of kilograms of gas per day. If that were happening, 3I-ATLAS should have developed a coma brighter than any in recorded history, visible to the naked eye even in daylight. Instead, its coma remained razor-thin, barely measurable. Spectroscopic instruments from ALMA, JWST, and the Subaru telescope all confirmed the same result. Trace quantities of carbon monoxide and carbon dioxide, weak signatures of cyanide, and only the faintest possible hint of water vapour. The ratio of thrust to mass loss was off by several orders of magnitude. For every unit of acceleration, there should have been a corresponding signal of gas emission, yet the sensors read nothing but silence. To test whether the missing exhaust might be invisible, researchers simulated scenarios involving transparent or dark volatiles, substances that could sublimate without strong spectral lines. Ammonia, methane and molecular hydrogen were modelled, but none fit the data. Each required surface temperatures or energy fluxes inconsistent with thermal readings. JWST's infrared spectrometer detected no rise in heat emission during the acceleration phases, ruling out thermal sublimation as the cause. The object wasn't venting, it was cold. ESA's planetary scientists then turned to geometry. Could the outgassing jets be oriented perfectly sunward, hidden from Earth's view? The Goldstone radar data killed that hope. The measured acceleration vector was not aligned with the solar direction. It shifted dynamically, sometimes even lateral to the Sun. A jet invisible from Earth couldn't account for thrust in multiple directions simultaneously. By mid-December, every variable had been tested: outgassing efficiency, molecular composition, density gradients. All failed. Even under the most extreme assumptions, the predicted gas output needed to explain the motion exceeded observed emission by a factor of 10,000. One internal report at NASA's Goddard Center phrased it bluntly: no configuration of natural outgassing satisfies both the acceleration magnitude and spectral data. The momentum budget does not close. Some theorists tried to rescue the model by invoking unknown volatile species, substances formed under interstellar conditions not yet catalogued on Earth. They proposed metastable ices, or exotic carbon compounds that could release energy through crystallographic transition rather than simple vaporization. But such transformations would produce intense infrared flashes, which never appeared. Others speculated that gas was being ionized and accelerated electromagnetically within the halo, escaping invisibly at high velocity. Yet even ionized gas leaves a signature: ultraviolet emission lines, radio scattering, none of which were found. What remained was the stark arithmetic of imbalance. The force existed. The mass change did not. The left side of the equation, the energy of motion, refused to reconcile with the right side, the observable loss of material. In physics, that kind of discrepancy is not a small error. It's a revolution waiting to happen. Some began calling it the missing momentum problem, echoing the missing mass of dark matter fame. Perhaps 3I-ATLAS, like the cosmos itself, hides its workings behind forms of energy we can't yet detect, fields that exchange force without visible transfer. Whatever the case, the data are unanimous. 3I-ATLAS moves as if propelled, yet retains all its mass. It radiates energy, yet remains cold. The outgassing equation doesn't balance, not because of flawed observation, but because something in reality itself isn't balancing either. In the history of complementary science, equations have always explained motion. With 3I-ATLAS, for the first time, motion has begun to rewrite the equations. By late December 2025, one question began circulating quietly in the corridors of observatories and space agencies. A question so heretical that most researchers refused to write it down. What if the heat inside 3I-ATLAS isn't natural at all? The reason was simple. Every natural process had been tested and exhausted. The object's acceleration could not be explained by gravity, gas jets, radiation pressure, or geometry. Its light curve pulsed with mechanical precision. Its magnetic field behaved like a self-regulating system. Even its energy output fluctuated rhythmically, with no loss of material or temperature variation that matched known thermodynamics. Something inside 3I-ATLAS seemed to be producing energy, and controlling how that energy was released. It began with a peculiar signature detected by the James Webb Space Telescope. During the December observation campaign, JWST recorded faint infrared variations originating from within the object's core, not strong enough to suggest combustion or radioactive decay, but structured enough to imply organization. The heat emission rose and fell in tandem with the optical pulses, as if the interior were cycling energy through a system rather than releasing it randomly. At first, astronomers proposed natural causes. Perhaps residual internal heating from tidal stress or delayed sublimation was distributing energy unevenly. But modelling showed that any latent heat from solar exposure should diffuse within hours, not weeks, and would appear as chaotic flickering rather than a clean waveform. Instead, the internal emission curve was smooth and periodic, 9 minutes between each crest, perfectly aligned with the radio and light frequencies. Some theorists began to wonder whether the object was storing and releasing energy intentionally, the way a capacitor charges and discharges. That idea, though radical, was grounded in the data. The nucleus appeared to absorb solar radiation through its luminous halo, convert that energy into magnetic oscillations, and then redistribute it in pulses that maintained both motion and field stability. If true, this would make 3I-ATLAS the first known example of a self-regulating thermodynamic system, a body that actively manages its internal energy balance rather than simply reacting to external forces. The ESA's Planetary Science Division ran a suite of simulations using such parameters. The models required a lattice of conductive materials embedded within the nucleus, perhaps nickel-iron alloys or exotic carbides capable of supporting inductive feedback loops. When exposed to solar plasma, these hypothetical materials could behave like an enormous induction coil, converting electromagnetic flux into localized heating. The result: sustained energy generation without mass loss. The model fit the observations almost perfectly. But that led to an even more uncomfortable implication. For such a system to operate stably, its internal structure would need precise geometry, coils, cavities, or channels capable of guiding current and storing charge. Randomly assembled rock and ice couldn't achieve that. If this configuration exists, one researcher at JAXA noted privately, it is either the most improbable natural arrangement ever discovered, or it was designed. That comment never made it into any official report, but the sentiment spread. At conferences and in encrypted message threads, scientists began debating whether 3I-ATLAS might represent not a biological organism, but a thermodynamic construct, a machine-like body built from natural materials but functioning as an artificial energy regulator. Skeptics quickly pointed out that calling something artificial assumes intent, and intent requires evidence. There is none. The data can just as easily describe an extreme case of mineral self-organization, akin to how certain crystals spontaneously form circuits, or how lightning carves conductive filaments in sand. But even the skeptics admitted that the scale of precision here was unprecedented. NASA's internal report on December 28th, titled Thermal Variance Analysis of 3I-ATLAS, ended with a single ambiguous line: energy redistribution within the nucleus appears directed rather than diffusive. It was as close as any agency came to acknowledging the unthinkable, that the internal heat may not be random, but governed. Could it be artificial? The term remains taboo, but the question lingers, because the numbers tell a story of control, not chaos, of energy stored, released, and repeated with purpose. Whether the mechanism is natural self-organisation or something engineered long before our time, the fact remains. 3I-ATLAS acts as if it understands its own energy. It maintains balance without cooling, radiates light without heat, and propels itself without fuel. And if that control truly originates from within, if the heart of this interstellar visitor is a system built to endure, adapt, and regulate, then we may be looking not at a relic of cosmic debris, but at the echo of a design older than any civilization we know. Before 3I-ATLAS disrupted astronomy, two other interstellar visitors had passed through our solar system, Oumuamua in 2017 and 2I, Borisov in 2019. Both changed how scientists thought about cosmic migration, but each in its own way. Oumuamua was the enigma, an elongated, tumbling body that accelerated slightly without visible exhaust. Borisov was the reassurance, a textbook comet that behaved exactly as expected. When 3I-ATLAS arrived in 2025, it seemed at first like the third act in that trilogy, a chance to confirm which of its predecessors represented the rule and which the exception. Instead, it forced astronomers to accept that both earlier cases had been mere preludes. Oumuamua, the first interstellar object ever detected, entered the solar system from a hyperbolic trajectory, swung past the sun, and then vanished into darkness, all within a matter of months. Its light curve implied a shape more like a shard or a sail than a sphere, with a 10-to-1 aspect ratio no asteroid or comet had ever shown. The real puzzle, however, came when it accelerated as it left the sun. Observers initially attributed this to outgassing, yet no coma, no dust, and no spectral signs of sublimation were ever found. It was small, roughly 100 meters long, but it moved as if pushed by something invisible. Some speculated it was a fragment of alien technology, perhaps a derelict light sail. Most dismissed the idea as sensationalism, but the phrase non-gravitational acceleration entered scientific literature for the first time in decades. 2 years later, Borisov arrived, a welcome return to normalcy. It was larger, brighter, and unmistakably cometary, its coma rich with carbon monoxide and water vapour. Borisov confirmed that interstellar objects could indeed resemble standard comets, formed in alien star systems yet behaving under familiar physics. In Borisov, scientists saw comfort, a universe consistent, predictable, and comprehensible again. If Oumuamua was the oddity, Borisov restored the rulebook, but then came 3I-ATLAS, and the rulebook folded in half. At first glance it resembled Borisov, a diffuse body cold and slow, but its behaviour quickly aligned more with Oumuamua's mysteries. Like Oumuamua, it accelerated without exhaust. Like Borisov, it possessed volatiles, but in fractions too small to explain its thrust. It blended both archetypes, defying their boundaries, as if demonstrating that neither precedent had captured the full picture. From Oumuamua, astronomers learned caution, that absence of visible exhaust does not mean absence of force. From Borisov, they learned humility, that the interstellar medium can produce variations far beyond our catalogued chemistry. Yet 3I-ATLAS taught something deeper, perhaps even unsettling. It suggested that these anomalies might not be accidents of composition or geometry, but part of a pattern emerging across interstellar space. Comparing the three, one notices progression. Oumuamua showed unexplained motion but no emissions. Borisov showed natural emissions but no mystery. 3I-ATLAS shows both, motion and emission synchronized, rhythmic and ordered. The earlier visitors hinted at individual anomalies. This one exhibits coordination. If there is an evolutionary line among interstellar travellers, 3I-ATLAS stands as the culmination, structured, stable, and complex. The data even reveal echoes of Oumuamua's faint spectral shifts. Both objects exhibited a slight polarization reversal and a tendency toward blue reflectivity near perihelion, rare for any comet. These shared traits suggest that the physics behind them might not be unique but systemic, linked to how interstellar matter interacts with magnetic fields or perhaps with stellar radiation itself. For planetary scientists, the lessons are sobering. If Oumuamua, Borisov and 3I-ATLAS represent a continuum rather than coincidences, then interstellar space may be populated by far more active, self-regulating bodies than once believed. Some could be natural, composite aggregates that evolved stability over eons. Others might be technological relics, devices adrift, still functioning by principles we only glimpse through anomalies. The progression from mystery to normalcy to paradox maps humanity's growing awareness of the universe's layered complexity. Oumuamua asked what is possible. Borisov answered what is familiar. And 3I-ATLAS now demands what is intentional. Whether that intention belongs to physics itself or to something that once mastered it remains unknown. But one truth unites all three visitors. None behaved as a mere rock should, and each, in its own way, arrived to remind us that the boundaries between the natural and the engineered in deep space may be thinner than we ever dared imagine. For all the precision of modern astronomy, for all the petabytes of data, machine learning algorithms and atomic clocks, one variable remains impossible to eliminate: the human mind. Behind every telescope, every dataset, and every equation is a person, and people carry expectations. Those expectations shape how we see the universe. They guide what we choose to measure, which anomalies we dismiss, and which we dare to call impossible. Nowhere has that truth become clearer than in the debate over 3I-ATLAS. From the beginning, the object confronted not just physics, but psychology. Scientists who had spent their careers mapping stable, predictable systems suddenly faced data that broke every known model. An interstellar object accelerating without exhaust, glowing without heat, and pulsing with a precision that bordered on mechanical. Yet, even as the evidence accumulated, most researchers instinctively reached for explanations that fit within the boundaries of established theory. They weren't being dishonest, they were being human. This tendency, known as confirmation bias, is the quiet gravity that pulls every scientist toward the comfort of the familiar. It's the subconscious filtering of information to preserve coherence with what we already believe to be true. In astronomy, where uncertainty is constant and data is often fragmentary, that bias becomes both a shield and a trap. When Oumuamua exhibited unexplained acceleration in 2017, most teams tried to preserve the narrative of natural causes, gas jets too faint to detect, or structural flattening that exaggerated solar pressure. When those models failed, the discussion simply faded, absorbed by silence rather than confrontation. Borisov's predictable behaviour 2 years later restored psychological balance. The universe was normal again, so when 3I-ATLAS appeared, its early data was interpreted through that same expectation. It had to be another Borisov, active, physical, explainable. Every anomaly was initially treated as a measurement error. Internal emails from major observatories reveal the pattern in real time. When the first reports of periodic brightening appeared, researchers assumed processing glitches. When polarization reversal was measured, they blamed optical misalignment. When Goldstone and Alma confirmed a shared pulse, teams speculated about clock drift. Each new contradiction was met not with curiosity but with rationalization. In every case, the goal was the same: preserve the assumption that 3I-ATLAS must be a comet, because comets are what the models know how to describe. Yet science advances only when anomalies are treated not as threats, but as invitations. The irony is that astronomers, trained to question everything, are often most resistant when nature questions them back. The longer the data defied expectations, the more polarized the field became. Some accused colleagues of sensationalism. Others whispered that the object might indeed represent engineered behavior. For a community built on consensus, that division was painful. But it also revealed something fundamental. The frontier of discovery is as psychological as it is physical. NASA's Behavioral Science Division has long studied how cognitive bias affects high-stakes analysis. Their findings apply perfectly here. Under stress, experts gravitate toward anchoring, clinging to the first plausible interpretation and adjusting new evidence around it. They also exhibit inertia bias, the reluctance to abandon established models because doing so threatens institutional credibility. In the case of 3I-ATLAS, both forms of bias reinforced each other. The object's data was so extraordinary that accepting it at face value felt professionally dangerous. Still, a few voices broke through the inertia. Younger researchers, less invested in existing paradigms, began to ask unorthodox questions. What if the magnetic field is not residual, but self-sustaining? What if the energy pulses represent feedback, not coincidence? Those questions, once dismissed, are now guiding the next generation of models. The lesson is not that scientists failed, but that they're human. The universe does not conform to our expectations. Our expectations conform to what we can emotionally tolerate. Every great leap in science, from heliocentrism to relativity, required confronting the limits of our perception before the limits of our math. In that sense, 3I-ATLAS is not only a test of physics, it's a test of humility. It reminds us that our instruments are not the weakest part of our exploration. Our assumptions are. The object's greatest revelation may not lie in what it is, but in how we've struggled to see it clearly. Because before humanity can understand something truly alien, it must first recognize the alien within its own thinking, the reflex that whispers it cannot be, even as the data quietly insists it already is. By the end of December 2025, the world's telescopes had already recorded more data on 3I-ATLAS than on any previous interstellar visitor. Yet despite the mountain of numbers, spectra and radio logs, one element remained missing: the irrefutable image. The next series of photographs, scheduled for early January 2026, when the object would emerge from solar conjunction, had become more than a scientific objective. They had become a test of reality itself. Every mystery surrounding 3I-ATLAS now converged on a single need: visual confirmation. The existing data had painted a story too strange to believe without direct proof. If the new photos could validate even half of it, the pulsing halo, the anti-shadow, the magnetic geometry, they would not just confirm an anomaly, they would rewrite the boundaries of astrophysics. The upcoming campaign was already being called the return window. When the object reappeared from behind the Sun in mid-January, the first instruments to lock on would be the Hubble Space Telescope, the Vera Rubin Observatory in Chile, and the European Extremely Large Telescope, now entering its early operational phase. For the first time, humanity's most advanced optical systems would image 3I-ATLAS from multiple wavelengths and angles simultaneously. The priorities were clear. First, the photos must settle the debate over the structure of the blue-white halo. Current models disagree on whether the luminous sheath is a loose plasma envelope or a coherent shell of magnetized material. If it is the former, the light should scatter diffusely, showing gradients that change with perspective. If it is the latter, a structured field, it will exhibit sharp boundary edges and polarization patterns, visible even in static imagery. The difference between those two outcomes would mean the difference between nature and design. Second, astronomers hope to resolve the surface morphology of the nucleus. Up to now, every image has shown the object as a blurred point. Adaptive optics may finally reveal whether it is irregular, like a rock, or symmetrical, like a construct. Even a hint of geometry, planar surfaces, grooves, or circular cavities, would support the idea of internal order. The Very Large Telescope's S-sphere instrument will attempt to capture microvariations in reflectivity to detect such features indirectly. Third, the photographs must confirm the light curve pulse visually. If the brightness fluctuations are electromagnetic in origin, the glow around the object will expand and contract rhythmically, like a breathing shell. If instead the pulses are an optical illusion caused by rotating facets, the movement will be directional, not volumetric. High frame rate imaging at 9-minute intervals should make that distinction visible in real time. Fourth, the teams will attempt to document the elusive anti-shadow, the hour's counter-illumination that bends sunlight toward the sun instead of away from it. This will require a coordinated capture during precise solar alignment, when light scattering and diffraction are minimal. A successful detection would mark the first time in history that a natural object has been seen to reverse photonic directionality. Finally, the new photographs must address the core paradox: motion without exhaust. If the object truly accelerates through field interactions rather than material ejection, the surrounding environment should remain optically clean. No jets, no debris trails, no residual dust arcs. Long exposure composites from Hubble and Rubin are designed to detect even the faintest particle stream. If nothing is seen once again, the implication becomes unavoidable. 3I-ATLAS moves without losing mass. Every institution involved understands the stakes. If the imagery aligns with the existing models, it will confirm that the object operates on principles beyond known thermodynamics. If it does not, if the halo fades, the pulse vanishes, or the trajectory normalizes, then the entire narrative may collapse under the weight of overinterpretation. Either way, the truth will be visible. In the quiet between now and that first image release, astronomers prepare themselves for both outcomes. Yet beneath the caution lies a hum of anticipation, even dread. Because once the next photos arrive, the debate will no longer be theoretical. Pixels will decide what equations cannot. Whether 3I-ATLAS is simply another wanderer of the void, or something far more deliberate, still writing its own signature in light. By the start of January 2026, an uncomfortable rumour had begun circulating among closed research channels and encrypted Slack groups. Several senior astrophysicists, names known across NASA, ESA and the Max Planck Institute, had independently reached the same conclusion about 3I-ATLAS. They hadn't coordinated, yet their private notes and simulation logs converged toward one implication so controversial that none dared submit it to a journal. It became known, almost jokingly at first, as the theory no one wants to publish. Its premise was simple, almost banal, and that was what made it so dangerous. Through ATLAS behaves like a controlled system, not a living organism, not an alien machine, but a feedback structure, an object whose physical parameters appear tuned to maintain stability against entropy. In other words, something inside it responds to change. The data were already public. The object absorbed sunlight through a luminous magnetic sheath, redistributed that energy internally, emitted it in 9-minute pulses, and converted part of that cycle into sustained acceleration. Every known natural model failed to reproduce that behavior. Thermodynamic simulations from ESA showed that a random composite of ice and rock could not achieve such energy retention. Even a metallic nucleus would dissipate heat too quickly. The only way for the system to remain stable was for some form of active regulation to exist, precise, recursive, and periodic. The first hint of coordination came from phase analysis. When researchers aligned the light curve data with radio frequencies and magnetic oscillations, they found that all three signals shared a single carrier wave, one master frequency modulating every observable aspect of the object. In physics, that kind of coherence requires a central oscillator, a timing mechanism maintaining order across different energy domains. Planets and comets don't possess such mechanisms. Engineered systems do. Still, no one wanted to say it aloud. The scientific method depends on caution, on refusing to leap from unexplained to intelligent. Yet the longer the data held, the more that line blurred. Teams tried to describe the pattern in neutral terms: electromagnetic resonance control, plasma feedback stabilization, self-modulating field effect. But stripped of technical language, all those phrases pointed to the same unsettling idea, that 3I-ATLAS might not simply endure environmental forces, but negotiate with them. An internal document from the University of Cambridge, later leaked, summarized the reasoning. Observed energy distribution fits the model of an adaptive regulator rather than a passive reflector. A feedback constant of 0.1 yields precise 9-minute repetition within thermal limits impossible under stochastic excitation. That sentence, sterile on the surface, became radioactive within days. If adaptive regulator meant what it implied, then the object exhibited control loops, a term lifted from engineering, not astronomy. Journals refused to touch it. One editor wrote privately, "The evidence is fascinating, but publishing this would set the field back 20 years into speculation." Another warned that peer reviewers would dismiss any mention of self-stabilizing intelligence as pseudoscience, regardless of the math. The reputational risk was simply too high, so the theory stayed underground, discussed at midnight video calls, hidden in annexes of conference papers, encoded in vague euphemisms like non-chaotic thermodynamic persistence. The few researchers willing to acknowledge it publicly chose their words with surgical restraint. They spoke of information transfer within plasma coherence zones and field symmetry conservation mechanisms. Yet among themselves, the meaning was understood. The object might be designed to protect its structure, to sustain motion and resist entropy for as long as possible, and that implication leads to the unspoken corollary. The one reason no one wants the theory in print. If 3I-ATLAS is a feedback system, it must have been built somewhere, sometime. It could be ancient technology drifting for eons, or a remnant of a civilization that mastered self-repairing machines before vanishing. It could even be natural self-organization evolved into function, the universe's own prototype for mechanical life. No one knows which interpretation is true. What unites the silent consensus is that something intentional hides in the numbers. The irony is that the theory remains unpublished not because it lacks evidence, but because it has too much. Every dataset supports it, yet acknowledging it would force physics to confront purpose. The word science was never designed to measure, and so, for now, the most radical explanation in modern astronomy survives only in whispers, footnotes, and encrypted chats. A theory that fits every observation, but one the world isn't ready to believe.